and welcome. And if you have questions along the way, please enter them in the chat and I'll try to monitor that and moderate as we go. And so I'll turn it over to you, Professor Kaelbling.
All right. Well, thanks very much for inviting me. And I'm sorry that we're not all present in the same room because I normally like to walk around and chat with people and make jokes and say silly things and so on. And it's kind of harder to do that sitting here in a chair, but we'll see what we can do. So let me go ahead and share my slides. Okay. Good. So, and then when I do this, I can see even fewer people. Actually, at least I can see some more of you if I do this. Okay. Because I like to see faces. So I'm actually, there are a lot of things to talk about. This is a 30-minute slot. I'm gonna just talk about a bunch of ideas that are relevant to the work that I do, and I'll try to stop in some places and we can have conversation. I understand actually it's a 60-minute slot, but I am supposed to talk for 30 minutes and you guys are supposed to ask me questions for 30 minutes. So we'll try to make that work out. Okay, so, people have been thinking about robots for a long time. And if you read the old literature, there's this idea that there's going to be these human level or better intelligent robots, and they're going to do all these things. If you look out in the world, it's still true that most robots are either welding the same thing every day in the factory, or they're a Roomba. So they're kind of simple in the way that they interact with the world around them. And right now, the research frontier is kind of at the level of, well, actually, now we have autonomous vehicles that are pretty good. They're maybe not completely autonomous, but they're getting better and better. And so the question is really, the thing that I think about all the time is, how do we get from Roombas to general purpose intelligent robots? And so really, this is my goal. I'm not trying to make robots in particular to solve a particular technical problem at the moment. I'm not trying to go to market with a robot, but I really want to understand AI in general, intelligence in general, and and then I want to test that in actual robots that can do things. I'm interested in robots that can do a wide variety of tasks. And in fact, I made a homework assignment for my class, I don't know, it was a year and a half ago or something. I had a seminar on intelligent robots, and the homework assignment was to go to somebody else's house and make tea without asking any questions. So if you think about that, you think about, okay, so I would like to make a robot that could go to anybody's house in the whole world and make tea. Pretty much everybody makes something like tea. They put some leaves in some hot water and let it sit for a while and they drink it later. But they do it in all kinds of different ways. They might make the water hot over a fire or in a microwave and you could figure it out. I suspect if you went to pretty much anybody's house, you could eventually figure out how they make tea. So think about what a robot would have to know and do in order to be able to do something like that. So that's what I want to do. So here's a picture that I like. I promise you it's not my kitchen. But you look at this kitchen, imagine the robot, you buy a household robot, you say, okay, robot, here's my house. The robot looks at this kitchen, says, oh my goodness, where is the fork? I don't know. So what would it take? It's terrible. I make terrible jokes and I don't even know if you hate me or not. But anyway, okay, here we go. Right. So where's the fork? I don't know. So how could you think about the difficulties involved in doing things in this kitchen? Okay, so actually, what I want to do is talk for a minute about how we even think about programming robots to do this. And I think some of you will actually, maybe you already know this and you'll explore it. But I had a conversation with some people from the military actually about autonomous weapons. And they wanted to ask me about how we program robots and stuff like that. And they asked me if my robot ever did something that I didn't expect. And I just burst out laughing because of course, like my robot all the time does things I don't expect. And for a little while, I couldn't even figure out like why they were asking me this question. And what I realized is that I think that they had a kind of a wrong model of how we program robots and AI systems more generally, right? So if you did like high school robotics or Lego Mindstorms or something like that, you'll be familiar with a kind of a model of programming, and especially programming robots where you say like, oh, go forward, say hello, turn left, do something, do something. And it's true that if your idea of how you program a robot is that you just give it a sequence of instructions, then it is kind of surprising that a robot would do something that you wouldn't expect. But like approximately nobody programs robots in this style anymore, right? It used to be actually back in the day, people programmed robots. And this picture is actually not that old. I just got it off of YouTube, but you know, this guy is programming the robot by like teleoperating it, and it's a nightmare. It's slow and difficult, and really nobody wants to do this anymore. So, okay, if that's not how we program robots, how do we program robots? And the way we do it generally is to say, here's a space of possible answers, possible solutions to my problem. Maybe if it's the robot moving through space, it's a possible space of possible paths the robot could take. I specify some kind of an objective function, like, oh, I like the solution better than that one. So I like solutions that don't crash into things better than solutions that do, or solutions that are short better than solutions that are long. And then I try to make an algorithm. I now, as the robot engineer or the AI person, I don't try to program the robot directly. I try to make an algorithm that's good at finding solutions that I like. So now I'm like programming at one level of abstraction higher than I was before. And now it's pretty clear that I could get answers that I don't expect. So here's just, you know, an example of pathfinding for a robot. Again, this is, I stole some videos off of YouTube and I feel bad because I should have credited this one, I didn't. But a standard algorithm for programming robot path planning is this thing called rapidly exploring random trees, or RRTs. And the idea is that it kind of, you know, it has to find a path that go around this obstacles, and it kind of randomly generates some points in the space that connects them together and tries to find a short path. And so this is something, if you're doing robot stuff over the summer, this is something you might be doing. So that's an example. And now with all the enthusiasm and hype and whatever about learning, we can think about learning in sort of a similar way. So Google, you know, does learning. Every kind of system you can think of now does learning somehow. You know, Facebook might predict whether you should be friends with somebody else. So let's talk a little bit about some intuitions behind machine learning, and then how you can formulate it as an optimization problem. So one idea is, you know, if Facebook might try to predict whether you're supposed to be friends with somebody else. I used to use this example a while ago and it would freak people out. I would tell a big group, like maybe this group, that, you know, some computer in California, for an arbitrary two people here that I don't know, Maya and Neil, some computer in California has asked the question of whether you guys should be friends or not on Facebook. And that's a little weird. And how does it do that? Well, it might formulate a description of a pair of people in terms of some features, like how many friends you have in common, or do you go to the same school? I can turn that into a vector. And then I can try to find some classification rule that would say, all right, I'm going to take this vector of features and predict yes or no whether you're supposed to be friends or not. And so I usually do this interactively. This is not going to work so well, but anyway, so just to get an idea of the underlying principles in some way behind machine learning, we can talk about the different sort of aspects of a problem that machine learning has to deal with. So imagine that I tell you that the things that I have two categories of things, and the things on the left are examples of the yes category, and the things on the right are examples of the no category. And now I ask you, is it a yes or no? I'm going to pick on Jennifer because I can. So Jennifer, is it a yes or a no?
I'd say it's a no.
Okay, it's a no. And probably in this case, right, it's a no because we can see right there, it's a no, for goodness sake. So one part of memory is remembering things. One part of learning is remembering things. And certainly people who have taken tests know that. Okay, that seems pretty good. All right, so here's another example. So here are some yeses and here are some nos. Is this a yes or a no? I'm going to keep picking on you unless I don't know someone else whose face I can see that I can yell at. So Jennifer, you're on.
So I'm going to guess it's more likely a yes.
Why?
Because there are far more blue squares in the yes than in the no.
Yeah, right. Okay, good. So this is the statistical part of machine learning, right? So sometimes you can just remember something, but a lot of what machine learning has to deal with is the fact that there's noise or some kind of errors in the data you're getting, or just fundamentally, you can't always make predictions right. Like Facebook can't always make predictions right about who's going to be friends. So some kind of statistical stuff is important. Okay, so here's another one. I got to pick on somebody else this time. All right, so here's some yeses and here's some nos. And here's a question. Blue arrow. Does a student want to answer? You could put your little blue hand up probably, or you could just speak. Or maybe I'm too terrifying. Aparna raised their hand. Aparna, tell us.
I think it's in neither of those because you never see a blue arrow in either the yes or the no columns.
Okay, that is an awesome answer. Actually, that's a way to say, you know what? I am not going to answer your question because I don't think I can do it reliably. Now, actually, we're really interested in getting machine learning algorithms that can do that, that can say, I'm really not sure. But in fact, most of the time, they got to make a choice, right? So Facebook is either going to predict that you're friends or not. Alexander, what do you think?
So I think it's gonna say the first one because there's more blue things as opposed to the second one, which has only one arrow and no blue things.
Yeah. Okay, good. So that's an answer. So you could say, all right, I think it's going to be blue because I think it's going to be yes because there's more blue things in the yes, and yeah. So right. So that could be good. But you know what? If these were cars, and you told me, and we were trying to make some prediction about whether they would be cheap or expensive, or I don't know, their gas mileage, and you gave me an argument about the color, I might not be so persuaded. So one thing that's really interesting is that usually the biggest problem in machine learning is this idea of generalization, that I have some data and I have to make a hypothesis, and the hypothesis is supposed to work well on data I have never seen before. That's the problem of generalization. And usually there are many, many hypotheses you can make that agree with your data. And now you have to say, well, out of all the hypotheses I could make that agree with my data, what's the best one? Anybody have an idea of like a principle that we could use for figuring that out? Oh, Brooke, this is fun.
I don't know, maybe depending on like the shape or the color, whichever one is more important in the instance, you could assign weights to each of the like different descriptions.
Right. Okay, good. Right. So that what you just said there is a really important idea, which is it helps to have some understanding of your domain. So it is the popular view in some ways of machine learning is that it's like a magic box. You pour your data into it and out comes a prediction that is really useful in the world. But usually it doesn't work like that. Usually you, the designer, the engineer of the machine learning system, have to actually put in some understanding of your own somehow. You might do it by weighting the features. You might do it by deciding what features to use. Like if you think color is totally irrelevant to the problem, you might not even make that feature available to the algorithm. So machine learning is an important combination of this combination of statistics and memory and generalization, but also the ability to leverage some structural or some kind of understanding of the problem that you have. So let's just do this one more kind of little exercise and then we'll go on to something else. So, okay, so here is some data and I might tell you the red ones are positive and the blue ones are negative. And I might ask you, what hypothesis do you think that you might use to separate the red ones from the blue ones? And probably a lot of people would pick something that looks sort of like that. You'd be like, okay. And by saying that that's a good hypothesis, you would be saying, well, and I think that the other points that are on one side are going to be, if you show me another point on that side, I'm going to predict that it's red, right? So, but now what if I give you this data? Well, if I give you this data, you might say, I think that's a good separator. There seems to be like kind of a curving boundary. So maybe I think that these are positive, these are negative, and that's probably a reasonable idea. So what happens if I give you this data? And now I want to volunteer. I sometimes see names on my screen. That's how I'm picking. I'm not sure what governs that, but Junha Huang.
You can probably draw a line sort of near the middle and take some of the points, like two red ones, and there's the red one, two red ones around the blue and the red one around the red, or
Yeah.
the blue one around the red. You can probably take those as errors and just ignore.
Okay, good. So that's one theory, is we can draw a straight line and say, we're not going to get them all right. Another theory, so we had two theories. Okay, so that was your theory, right? That was I've already forgotten your name. Sorry, Junho. No, I don't know. Okay. So one theory is, we should just have this nice, simple, linear description, but we should make some errors. That's okay. Everybody makes some errors sometimes. Another idea is, no, look, we can get this right. We just have to have a more complicated theory. And which one is right? I don't know. It's not really an answerable question. Which one is right depends on your problem and what you're going to use it for and what you understand about the kinds of things that you've seen and whether you think your sensors really do give you noise and all kinds of things like that. So this is like, if there's a fundamental tension in machine learning, it's this one. It's like, should I have a really complicated hypothesis that gets all my data right? Or should I have a more simple one that gets some things wrong? And so there's beautiful math about it. There's lots of algorithmic stuff about it. It's an important question. Okay, so that was a little digression on machine learning because I like teaching machine learning. I teach machine learning to like 600 undergraduates, many semesters lately. So what we were talking about was how we design programs in AI. And I said we designed it often do it by saying a space of hypotheses. So imagine that I want to find faces and images. This is like kind of a passé machine learning problem, but it's still a machine learning problem. So we could say, okay, what we're going to do is my hypothesis space is going to be that I'm going to take a chunk of pixels in the image. And we can take that chunk of pixels and interpret them as a bunch of big vector of numbers. And I'm going to compute some function of the input vector. And if it has some property, then I'm going to say that's a face. So here I described like a linear function. If you know about neural networks, then it would be a fancier function, but the idea wouldn't be too much different. So our possible solutions are going to be vectors of these numbers W. Those are parameters in our answer. And so what we're going to do is we're going to try to find some weights, some values of those parameters, so that given a bunch of training examples of boxes with faces in them and actually boxes without faces in them, we classify a lot of them reliably. And the way that we try to find that is by searching in the continuous space of, let's say, 10,000 dimensional vectors of numbers. And generally we do it by trying to just walk up the hill of the objective function. So this is another example of a case where humans are terrible. Humans tried for years and years and years and years, very smart humans, tried to write programs to recognize faces and none of it worked. But as soon as they started writing programs to take data in and convert that into a program that recognized faces, then it started to work. So it's a similar story to the robot planning thing. Okay, so let's go back to my robot. That is my robot. it's a kind of an old robot now. It's kind of falling apart. One of the hands doesn't work very well. It's very sad. But anyway, okay. So the problem, imagine the problem of the robot having to clean that kitchen. So people who do robotics like to talk about configuration space. The configuration space normally is just the joint angles of your robot. Like if I want to describe how my robot is positioned, I can say, oh, the base is here in X, Y, and rotation, and each of its joints has some angle, and together that's a configuration. And they like to talk about, oh, this problem's hard because my robot has a lot of degrees of freedom. It has a lot of joint angles, let's say. But if you think about this kitchen is really hard, and it's really hard because how many degrees of freedom of the kitchen is there, right? How many variables, dimensions would it take to describe what's going on in the kitchen, right? And it's not just where are all the objects, but it's all these things, right? Are the dishes clean? Is the stove on? Could you eat the stuff that's in that blue bowl, right? These are all parts of the state of the kitchen. And there's too many to count, right? It's very difficult. So yeah. Another thing that makes reasoning and planning problems difficult is the horizon, right? So how long is the plan? So if I have to plan a two-step, if you have 2 errands to do, it's pretty easy to figure out what order to do them in. You just have to think about 2 orders. But if you had 10 errands or 100 errands, it would be very difficult. This poor robot, right? It has like maybe 10,000 little teeny steps it has to do. And there's like no way that you can come up with a sequence of 10,000 small steps. So that's really hard. So we have to take the big problem and somehow make it into smaller problems. And the final thing, big class of things that makes this problem hard is uncertainty. And lots of robotics people, if you say, oh, I really care about uncertainty, they say, well, if you just buy better sensors, you wouldn't have to worry about uncertainty. You would just know what's going on in the world. But I think that's actually completely wrong because better sensors won't tell me like what's inside that blue bowl or what's in your head. So there are things, aspects of the world around me that I really just don't have a good insight into, and I can't get by improving my sensing. So what's in the what's inside this Tupperware, or when are the people coming home, or what would happen if I did this thing, right? So you have to really worry about uncertainty. I'm going to skip this. Let's see. And I'm going to tell you something about this robot. I'm just looking to see what my timing's like. Okay. Actually, let me stop for a minute and see if there are questions about let's go here. Questions about the learning stuff or the planning ideas or what my poor robot has to do in the world. So we can do some questions and then I'll go on.
Anyone have questions they can enter into the chat?
Or I can't really see the chat reliably. Also, probably you could raise your hand or something.
Sure. Okay, Emma, do you want to ask your question? Emma Jolie?
Yeah, my question was, so what can you do to kind of work around that uncertainty or kind of like make your function more versatile or robust? Yeah,
okay, good. So what do we do about this kind of uncertainty? And the answer is that it's common if you think about robot planning, the easiest thing is to say, oh, the world is in some situation and I know what it is, and then I'm going to take an action and the world is going to change and be in a different state. What we do is we do that kind of planning, but instead of planning in terms of states of the world, we plan in terms of states of the robot's mind, the states of the robot's belief about the world. So we might say, oh, the robot knows what's on the counter, but it doesn't know what's in the refrigerator and something, right? So that's like what we call a belief state or a knowledge state. And then we can say, given what the robot knows, what action should it take? Maybe it can go and wash the dishes because it can see the dishes and understands what's going on with that. Or it might say, I need to find a sponge. I don't see a sponge. I don't have information about where a sponge is. But maybe I do have information that they're often contained under the sink. And so then I'm going to go, the robot could then decide explicitly to gather information by like looking under the sink to see if there's a sponge there. So the key is really embracing the fact that you're uncertain, really acknowledging that fact, and then explicitly planning to gather information to get rid of the uncertainty. The other thing, though, that's really important is that you don't want to bother getting rid of all of your uncertainty, right? So you could spend a ton of time like counting how many threads there are in the carpet or something, and that would reduce the entropy of your belief about the world. It would help you get more information about the world, but it wouldn't be useful. So what's really important is gathering information, but gathering information in a way that's driven by what you're trying to do.
Do you want to take another question?
Sure.
Okay, so Washang Sun, I'm sorry if I pronounced that incorrectly. Do you want to ask your question?
Yeah, so I'm wondering what your opinion is on the general AI. Do you think it would be dangerous? Because I could easily think, for example, if we ask the robot to heat up a cup of water, the robot might think, oh, lighting up the house might be the fastest way. But so I understand that we can limit the amount of things that the robot can do, but without understanding, like without humans understanding every possible like outcome, how do we know that the robot will make a decision that we don't even might not know yet is safe?
Yeah, no, that's a really great question. And I have two kinds of competing feelings about it. On the one hand, if you came and saw my robot, and I'll show you some videos, I'm very proud of it. It's a very good robot, but it is not going to take over the world anytime soon. So there is that. But I do think that there's this really interesting question of how to manage this. I mean, there's this problem that in some sense, when you ask the robot to do something for you, right? You say, robot, make me a sandwich. You don't mean make me a sandwich at all costs, right? And so the question is, can we as engineers in advance program in some guardrails or general utility function for the robot that says, oh, when I ask for something, I ask for it, but subject to a bunch of constraints about safety and so on. And one interesting thing is, you know, I kind of talked at the beginning about how we often frame problems in terms of specifying an objective function. And now, in fact, if that's really how you specify programs, and you're pretty good at the optimization part, then the debugging loop is going to be about debugging what you ask for, right? So you always, you know, people always talk about, well, you should be careful what you wish for, right? So you need to be careful what you ask the robot for. And there are people thinking about how to do debugging of an objective function under constraints that the overall system is safe. So I agree that that's really an interesting and important problem. And there's probably some technical ways that we can help with that. Yeah. Okay. I will go forward a little bit and then we can stop and take some more questions. Well, let me describe this. So what I've been working on for quite a while, I'm going to talk about a little bit about planning type stuff and a little bit about learning, is planning. So not really worrying about learning, but trying to understand what we can do as engineers. And I'm showing you some examples here, and I'll show you some more in the next slide, that they're somewhat entertaining because they were proposed as a suite of problems for robot learning. And the idea is that robot would learn to do each one of these things. And then after it learned to do several, the hope is that maybe it would learn to do another one more efficiently. But the fact is that with planning, we can just do them all. If you know enough about the state of the world. And we can do it by doing a kind of abstract reasoning and then a more detailed reasoning. And the abstract reasoning involves coming up with a set of categories of things that the robot could do. They end up getting called modes or mode families. So in this case, the categories of the thing the robot can do are like move through free space. It can pick up an object and then move around the world while it's holding that object. Put it back down. Once it puts the object back down, it goes back into the free space mode. It can push things and it can operate things. Here, there are some things that are like turning a handle or opening a door involve interacting with another kinematic mechanism. But what's interesting is, as a job for the programmer, once I program some things just about each of these 5 mode families, then my planning algorithm, then I say what I want. I want this object to be here or the water to be turned on, and the planning algorithm can figure out what to do. So I spend time thinking about how to structure a problem so that what has to be specified is relatively small, because I do hope to be learning those things in a little while. So there's some of these problems, and here's another set of them. They're not playing, they're playing. So I don't know, it's just robot doing a bunch of things. Okay. And we've taken those same ideas and used them to program an actual robot. So this is the actual robot, and I'm going to show this robot doing a bunch of things. And for any one of the things that this robot does, like 2 of you guys in a month or 2 weeks could program it to do it better. But the same program did all these things, and that's what makes us happy. So it's a pretty general purpose thing. So here's a case where we told the robot we wanted the blue box to be where the can is. That's all we told it. And it figured out that it had to move the can out of the way and get the box. Here we told it we wanted the green box to be on the edge of the table. The green one is too big to pick up. It figured out it had to pick up the green one. It also knows that its pushing is pretty unreliable. So after it pushed, it looked to see if it worked out. That was uncertain, and it wasn't. So it pushed it again until it was there. Here we told it to go out of the lab, but we put these chairs in the way. It didn't know they were there, but it knew about chairs. And here, it went out of the lab and it just brought a chair with it. Okay, so that's an example of, it did something we didn't expect. Here we asked for a full oil bottle to be on the other table. It picks it up to see if it's heavy. That's how it figures out if it's full. This is a kind of a random demo that's just in there for not really a good reason, but there's one more that's kind of entertaining. Here it's allegedly, oh yeah, this is the same code actually running on a different robot in Singapore even. So same idea. Okay, so this is a system that a colleague of mine and I built, mostly programmed it ourselves. And it's pretty good. It's pretty good. But there's no learning. And the only learning that got done here was by us, not by the robot. So now the question is, can we learn some things that will integrate well with the rest of the system? So if you look at most of the work right now on robot learning, it's focused on learning very kind of short horizon and difficult sensory motor tasks. Like you may have seen in the news, there's a robot that can manipulate a Rubik's Cube in its hand, which is really hard. And they did an enormous amount of learning and simulation, and then they ran it on the robot. And maybe I could, that way I could learn to reorient my pencil and my fingers. So that's all good. But that learning stuff really can just address one thing. It can be kind of complicated, but the space can't be really, really high dimensional. And so, and they tend to approach every problem as if it's completely new. So imagine that, I figured out how to do this, and in the course of that, it seems like I've learned a lot about how my fingers work, and I ought to be able to, like, I don't know, pick up another object and do stuff with it. But in many cases, most cases right now in robot learning, that would just be a new problem. And the robot doesn't know its own kinematics or anything. So we have been focused instead on what it might be like if you came to my house and you were a robot, and maybe you didn't know how to solder, or maybe you didn't know how to beat eggs. And I said, oh, okay, capable robot, I'm going to teach you this new thing like soldering or egg beating. How could you learn that and then integrate it into everything you already know, as opposed to learning it like just from scratch as a completely separate standalone thing? So that's the setup. Let me just look at the time. Okay. So imagine that we've already learned a kind of a closed loop controller for pouring, right? So we've practiced pouring in the bathtub or wherever robots would practice pouring, and robot knows kind of how to pour. But now what we're interested in doing is learning some kind of description of that pouring ability so that we can use it in the context of stuff we already kind of know how to do. And so I'm not going to talk to you about this in complete detail, but the intuition is that there's a set of variables in the world that govern whether the pouring is going to work out well. And it might be some kind of parameter like a gain parameter in the controller. It might have to do with how I'm holding the thing I'm pouring from, the shapes of the objects, the relative positions, and so on. And if I could learn a constraint, if I could learn a relationship among those continuous parameters that says, oh, if this relationship is true among all these parameters, then the pouring is going to work out, or, oh, no, it's not going to work out, then I can take this kind of package of information and put it into my planner, and the robot can use this pouring operation. So what we do is we use a machine learning method to take a lot of examples of pouring and try to learn when it's going to work out well. I don't have time to talk about this in detail, so I could come back to it later if I wanted to. But okay, stuff works better than it used to. I'm skipping this. Okay, so let me just show you this because it's fun. So we were here working on training the robot to do pouring and scooping. The actual robot, those are little scales. So one thing that's interesting about this is that it's really tedious. So we had to go and pick up chickpeas from the carpet and the lab. And actually we were away from the lab. Okay, this guy's too noisy. We were away from the lab for 3 months, and a postdoc just went back and the mice had been eating the chickpeas, and that was bad news. So yeah. But okay, so it's kind of difficult to acquire the knowledge that you need to do that. So it's really good to minimize the amount of experimentation you need. All right, so here, but after we learn some of these operations, we can put them in with the stuff we already know how to do. So here's the robot now. We put stuff on its table. For right now, it has to be those objects or some objects like that, but you can put them anywhere you want. You can give it any goal you want about how objects are related to each other on the table and about what's in them. And then it's using a planner to decide which object to pick up, how to pick it up, how to move its arm while it's doing that. So there it moved the green thing out of the way, and then it's going to come over and pour stuff. It's serving it to you on that tray. That's just a picture of a tray. Here it's supposed to put this thing on here and then put some stuff in it. And I want to show you one more example and then we'll go on. I like the next example because it was supposed to put stuff in that red bowl, but it couldn't reach to pour all the way over there. And so it figured out on its own that it should move the red bowl into the space where it could work more conveniently and therefore pour stuff into it. So I don't know, we think that that's cool. Inside a kind of general control architecture for a robot, right, that might do some perception, to integrate the perception it's had over time into some estimate of what it knows about the world, planning problems, low-level motor controllers. There's all kinds of different things that you could build machine learning algorithms to help you with it to make this thing work out well. Okay, so I want to leave time for questions. I'm going to let you watch some robot bloopers and you can ask me stuff.
Okay, great. So what questions do the students have? I am unable to see the hand raising that I think Joel is able to see. We'll start with Wenson Tang. Winston?
Does the robot only move one hand at a time? Because it seemed like when it was moving the bowl to the middle where it could reach, it was only doing everything with one hand, like, and the other one wasn't moving.
Right. It is entirely capable of moving both hands at once, but we sort of lazily just have it set up to do one at a time. So you could come and make it better.
What about Matthew Ho? Would you like to ask your question?
Yeah, so earlier you talked about you need to determine which types of uncertainty are important and which types are not important. How does that happen? How do you determine that?
Right. Well, the way it works in our kind of reasoning system is that imagine that it's trying to make you coffee, and it says, all right, well, I have to get some coffee into your cup. And it might say, okay, well, to do that, I have to be holding the coffee pot. And then I might say, well, to be holding the hot coffee pot, I need to know where the coffee pot is. And then it'll go look carefully at the coffee pot so that it can grasp it reliably, so that it can pour the coffee into your cup. But by kind of, at least in our system, it actually reasons backward from the goal and says, what information do I need in order to make this thing true? And then it will work to get that information.
So it actually like problem solves, I guess, in terms of like it realizes like what you actually need to do in order to get the goal. Okay.
Yeah, that's right. And it does it does this at a hierarchical level, right? So it might say, oh, at the highest level, I have to figure out what cupboard this thing is in. And then once I know basically where it is, then I can plan in more detail, let's say, to go grab it. So, yeah.
Thank you.
Sure.
Okay, Needy, would you like to ask a question?
Yes. So my question is, when we're talking about like a robot coming to someone's house, seeing a function happening and then mimicking that function, do we have to tell the robot explicitly to start mimicking that function? Or does it happen like the robot notices something in its surroundings happening repeatedly and then takes care of it or then copies that function?
Right. Okay, that's a good question. I mean, in my dreams, it would be just like, having a very helpful and observant and clever person coming to your house. So, at the beginning, and it depends. Like, so for instance, if I make pasta every day and you watch me, and then finally one day I go one more time to put the hot water on the stove, you might go get the pasta out of the cupboard, right? So maybe you could just induce that that's a thing that every time I get the hot water, I need a pasta box, and maybe you would go get one. So that seems like that should be able to happen without even any instruction. On the other hand, if I was trying to teach you a whole new skill, like soldering, I might have to tell you some stuff, right? Or at least it would go a lot faster if I told you some things. Like, oh, this gets hot and I hold this metal and it melts and you have to be careful that it doesn't do whatever, and also don't burn yourself. So, but you would like those interactions to be kind of fluid and for the robot to be robust, so that if a human helps it, it will learn faster, maybe, or break fewer eggs. But hopefully, maybe by trial and error, it could do it on its own. I don't know how to do this. This is just what I want. Yes.
Mm-hmm. Thank you.
Sure.
Charlotte, do you want to ask your question?
Wait, I'm muted. Sure. I was wondering whether you guys trained the robots in a virtual environment first before being implemented in the actual lab.
Right, good, because of all those chickpeas. So it's interesting. We do everything in simulation first, especially for debugging, right? So just to understand that the basic algorithms are right, because they usually, of course, aren't right for a long, long time. Mostly they're wrong in some way. So we do all of the debugging in simulation until we have something that looks like it might sort of work. For training in simulation, it's super tricky, because one thing about machine learning is that it will learn to exploit any property. It's made to exploit the properties of the environment it's in. That's what its job is. So if there's any weirdness about your simulator, there's a good chance that if you train something inside the simulator, it will learn to depend on the weirdness in your simulator. And it's very hard to simulate some stuff. Like, actually, I mean, I had students who spent a ton of time trying to just make a simulator that would simulate the pouring. It's not that easy, and the simulator is kind of slow. But what people do who do a lot of machine learning, especially, I mean, this Rubik's Cube in the hand example is a good one. I should have had that movie. They do something they call domain randomization. So there, the idea is, I want to make a simulation of the world, but I know I can't make a really accurate simulation of the world. I just give that up now, you can't do it. So what can you do? What they do is they have, you could think of it as like a whole ensemble of simulators, like maybe 100 or 1,000 variations on the simulated world. They change the frictions of the objects, they change, I don't know, the sizes of the fingers. They change not only the magnitude of gravity, but the direction of gravity in their simulator. And they look, and it was OpenAI. So they spent like, I want to say 70 CPU years. I mean, I don't know, like just an unthinkable amount of computer time trying to find a strategy that works in all those, one strategy that works in all those simulated environments. The premise is then, if it works in all those environments, it will probably work in the actual world too. So yes, you can use simulation, but it's not easy.
Okay, Ines, would you like to ask your question?
Okay. So my question is, what sort of input does the robot get from the outside? So is it just the camera and the weight sensors on the hands, or are there other?
Yeah, so this particular robot gets, and actually you can't see it in this picture, but it has a Connect sensor up higher on its head now. So it gets, and so a Connect sensor gives you a camera image, normal camera image, but also a depth image. So it tells you for each pixel actually how far away it is, reasonably, reliably. And that's hugely helpful. That really changed everything for robotics, was getting reliable depth sensing. It's true also in autonomous cars. So being able to measure the depth to things helps understand the shapes of the objects, helps understand what you're going to crash into and not crash into, and so on. It has some tactile sensors in the fingers. They are often broken, but they're still, they're useful. It has a force torque sensor in the hand, you're right. It can measure also how much torque it's expending at its motors, and sometimes that's useful. So that's pretty much what it has.
Okay, Graham Wilson, would you like to ask your question?
So my question was, what is the current limitation of AI and robots? Is it hardware, like if you could have, or sensors, if you could have better compute power and more accurate sensors, or is it totally software?
I would say that it's mostly software, or ideas even. There's a really great example of, there was for years, robotics people were like, oh yeah, we can't really do this because the hardware is not good enough. But there's a great video of actually a precursor to this robot that a human teleoperated to like clean up a house. And you're like, well, okay, if a human could teleoperate that piece of hardware to do this job, then it's a software problem. So I think I mean, obviously better sensors would make everything easier and better and more fluid and more elegant, but we could do way more with the hardware that we have.
Okay, Aditya?
So I was wondering how much time is sort of spent training the robots versus actually writing the code for them?
Right. Well, so in that first big video I sent you, there was no training at all. There was no machine learning. So that was code writing. But an interesting question to ask about the code writing, and then I'll talk about training. An interesting question about the code writing is how much of it was about this problem and how much of it was general purpose reasoning, right? So we try to make our trade-offs so that we build tools that are pretty general purpose, That's why the same code could basically run on different robots or make the robot do pretty different stuff. And that same code could be used to, I don't know, control different kinds of physical systems. And so we try to spend time on stuff that's general more and less time on stuff that's specific if we can. And that helps us build tools that are more useful. In learning, because this is research and much of the work we did was on developing the strategies for learning and so on, I would still say that, I mean, we spent more time on code than on learning. But again, we hope that those learning paradigms that we invented could be used more broadly, and then the balance would shift, because if they're still useful as learning methods, then you would spend more time learning and less time coding.
Okay, maybe we have time for just maybe one question, maybe two. Andrew, would you like to ask your question?
Oh, yes. Personally, are there any implementations you would like for a general robot to accomplish in a real world setting?
Any implementations? Do you mean like any, like a software module that would be particularly useful? Is that what you mean?
Yeah, like personally, like I'm sure it can do much more than just like making cereal, right, or something.
Well, I mean, again, my dream is a very general purpose robot that could do what it needs to do, right? And could see what I seem to be missing and help me out. And so I think rather than thinking again of like, oh, this is a robot that could make coffee or make cereal or do some specific thing, the really, really driving question for me is, what is like a basis set of abilities such that if you had that basis set and a general purpose strategy for putting them together, you could do all the things.
Oh, I see.
That's what I really want.
Thank you.
Sure.
Okay, so I think we're going to need to wrap it up here. This has been a great talk and fantastic questions. I'm very, very pleased to see everybody so engaged. So I'd like to thank Professor Kaelbling for her talk today. And now I'd like to turn it over to Lisa, who I think is going to highlight a couple students.
Hi, so we're going to pull up Matthew Ho and Rishna Gupta. So Joel, I'm not sure the best way to do that. So they're going to present a t-shirt virtually to the professor, and I am going to cover my face and hopefully I get all of the logo in.
Oh, here, let me unshare. Ooh.
Yeah, and let me remove my background because it is not liking it. Okay. All right, there is Matthew and Rashna. So here is the t-shirt. If you can all see it, the same one that we all have. And Matthew and Rashna, do you have anything you want to say?
First of all, just thank you so much for taking the time to speak with us, Professor. I found your seminar fascinating, especially the part about multimodal motion planning.
Cool.
Yeah, thank you so much. I was really amazed by, the fact that you can use the same piece of code to do like totally different things. Like, you don't need to modify it. It's not even specialized. We really appreciated your talk. We wanted to present you with this nice t-shirt, I guess, that you'll probably be receiving in the mail.
Yeah, cool. Thanks a lot. And I hope you guys have a lot of fun over the summer and make cool things. And hopefully, we could meet sometime in the actual physical world.
That would be great.
Yeah.
All right.
Excellent. Thank you so much.
All right. Bye.
Don't
Bye now.
disconnect. So we can just use this few minutes